want to talk about general relativity and the misunderstanding of Einstein. And now, one thing I've done is study the history of science. Unfortunately, we have too many reporters in the popular science press today who know nothing about science. Their only interest is to write a quick gee-whiz article in something like Discover magazine, where they had two articles promoting an alleged new attempt to redefine gravity, where they say that basically one scientist is trying to state that after you get so far away from an object like a galactic nucleus, then Newton's law breaks down, the F equals ma equation, and then it can be modified. Well, in college we used to call this the Schwanz factor. If an experiment didn't work out, the guys who just wanted to slide by in the experiment in the lab would add in a factor somewhere in the middle of their lab write-up and hope that the teacher never found it. That's what we have here, with somebody trying to just arbitrarily introduce a factor in the gravity equation of celestial mechanics and say, well, it kind of solves some of these problems, so let's include it. Well, that's bad science. Bad science, bad science. No two ways about it. Like I say, in college, that's what we call the Schwanz factor. There are other attempts to solve the issues, the dilemmas of modern cosmology, but let me talk basically in general terms so that you can understand this, what the issue is about. Back in 1905, there was special relativity had already been published. The greatest result of special relativity was that if an object was moving away from you in space and it was giving off light, you would see a red shift. In other words, the light that was emitted from the object, as if it were standing still relative to you, had a certain frequency, had a certain spectral characteristic, it had a certain color. If the object was moving away from you, that same light would look a little bit more reddish. If the object were moving towards you, it would look blue, or it would be blue shifted, as we call it in physics. So the frequency changed. The speed of light, however, remained the same, which was one of the oddities explained by special relativity, and this could be verified in many in-laboratory experiments. The Mossbauer effect, many experiments have been created, very innovative experiments, which show us, in fact, that special relativity is real. And it was the insight of Einstein that put together many topics of the day and simplified and found the key that unlocked the entire issue of the workings of light in the cosmos. There was the Michelin-Morley experiment, which also dealt with special relativity, and then Einstein generalized this into a theory called general relativity. Now, the main results of general relativity are as follows. Relative to light movement, in other words, the path of a light, if you had nothing else in the universe, the path of light would be a straight line, as we define it. But if you put an object in space, and that light attempts to pass around that object, it would bend according to general relativity. And Einstein did a thought experiment, what they in German called Gedanken experiment, a thought experiment. And here's how it goes. It's the famous elevator analogy. And this is the basis, get this, the basis of general relativity. There's no experiment that has proven general relativity directly in a laboratory. This is a Gedanken, a thought experiment. And here's how it goes. If you are in an elevator, physicists love to do experiments, thought experiments in an elevator. Anyway, Einstein said, imagine you're standing on Earth. We're going to do two similar experiments. One, you're standing on Earth or on a planet or on a star or on a very dense stellar object. And okay, and you are doing some light experiments or throwing a ball up and watching it come down. You're doing all your physics experiments. And then you put another guy over here in an elevator out in outer space, and he accelerates up. You put a rocket engine behind him, and he accelerates up at the same rate that gravity would pull you down on this celestial object, the star, planet, whatever you're standing on. Now you do all your experiments on the planet or star that you're standing on, and you do all your experiments in the elevator that's accelerating, and you watch the results. And if you look in the elevator and you shine a light through a little hole in the side wall of the elevator, then because you're accelerating, it would not hit the wall directly across from where the light beam entered. It would hit the wall on the far side just a little bit down. And you would see, if your detector was there, you would see the light beam bending down as if it were bending in a gravitational field. So by the elevator analogy, Einstein reasoned that light should bend in a gravitational field. And so this is where space-time warping comes from, the idea of a black hole, an object so massive that light cannot escape. And so there are two alleged effects of general relativity. One is that light would bend around a dense object, and light leaving an object would be pulled back, giving it less energy and creating a redshift. So there are two effects. And now this is boiling it down for the general public, and you can take all the tensor analysis, all of the complicated mathematics, all of the string theory, etc., and all the very complicated journal articles, but you can boil it down to these two very basic principles. That general relativity predicts that light should bend around an object, and that light leaving an object should create a redshift. However, when you look at the data in space, the data doesn't add up. And one of the first data sets that didn't add up was the data set relative to spiral galaxy arm formation. In other words, astronomers, if you look at a galaxy, it has those beautiful spiral arms. Astronomers assumed that those arms were moving around the galactic nucleus in circular orbits. In other words, that each star would form its path would form a circular path around the nucleus of the galaxy. And so when astronomers then pointed their telescopes to the galaxies and started to measure the redshifts of the stars moving around in the arms in the galaxies, they found out that the redshifts didn't add up. It didn't match the theory. And so neither general relativity could explain that, because the stars were not massive enough to create redshifts, and the special relativity theory, which also predicted the red and blue shift based on the movement of stars, you could see the red and the blue shifts, but they didn't fit the theory. The curve on the graph did not fit. When you plotted the data, the real data versus the theory, they didn't add up. Just to give you an example, then, by the way, this is published in my Planet X Comets and Earth Changes book. I published an article in 1979 which not only developed a galactic evolution theory which talked about the symmetry in the galactic arms, but it also showed how this new model would explain the light curves without using any fancy new equations, without assuming that there was matter in the arms, unseen matter. So let me talk about the idea of dark matter for just a minute. In the expanding universe, the Big Bang concept of the universe, where astronomers look out and they see everything is redshifted, everything seems to be moving away from us. So they assume that at some point everything must, if you reverse this in time and look back in time, then everything must have been in one small spot where an alleged Big Bang occurred. But there are great problems with this. We have objects called quasars, which are the brightest objects in the universe, allegedly, because they are the farthest objects away. They have the highest redshifts. There's a constant called the Hubble constant, which